This is FM21, paper 42, question 7. And this is a question about operational amplifier. So 2021 will be the last year where op-amps are asked in the A-level syllabus. It is being phased out by CIE. If I were to guess why, maybe because the circuit is kind of outdated. We have better circuit. You know, you have the Apple M1 chip. This is like the great-great-great-great-grandfather of the Apple M1 chip. But anyway, it's always good to know where the basics come from. So in case you're preparing for your exams, not just watching this to learn, there are 3 types of operational amplifier that is still covered in the 2021 syllabus. Okay, after 2022, there will be a refresh. So for 2021 syllabus, the op-amp, we have the comparator circuit. Okay, so we have recorded quite a few examples. Don't remember to check out the playlist, okay? To the comparator circuit, the inverting amplifier, and the non-inverting amplifier. So remember to know how to differentiate these circuits. You know how they look like, you know how they are different to each other, and also you know how to analyze them. So the skills that we are looking for is for you to be able to identify this circuit, all right, and also to be able to analyze. So most of the time for comparator circuit, the analysis involves a potential divider. Actually, they all involve potential divider, but it is more important for the potential divider circuit, okay? And for the inverting amplifier, the gain will be negative RF over Rin. So, or R1, this RF is oftentimes the resistor that is connected to the feedback loop. I'm going to highlight the feedback loop in this resistor now. So when we say feedback, right, it means that there's an output and then there's an input. So this is the output. The nose of the amplifier is the output. I'm just going to label this. This is your Vout. When part of that Vout, not all, because some of the Vout actually goes straight. So when part of the Vout is sent back into this part here, this is what we call a feedback loop. So this will be my RF. Okay, the non-inverting amplifier, your G is equal to 1 plus RF over R1. So this R1 is the other R lah. So how do we identify whether it's inverting or non-inverting? You check the ground. Okay, but I'll talk about that later. The third skill you need to know is to sketch the Vout. Okay, be mindful of the saturation that is based on your power supply, this number and this number. So the saturation in this one will be 3 volt, but it's actually going to saturate at the supply voltage. So check out these other circuits if you don't know. But part 1, name the type of amplifier. So the way you can identify inverting and non-inverting, right, is look at the ground. Okay, so V plus, which is this one, this is V plus. V plus is not grounded. So this is non-inverting. So a quick way to identify whether it's inverting or non-inverting, you check the non-inverting input V plus. If V plus is grounded, grounded here means connected to the ground. So your op-amp will be like this. This is plus, connected directly to the ground. V plus grounded. And of course goes without saying that there must be a feedback loop. So got feedback loop and V plus grounded. So something here that will feed it back like this with the resistor, something like this. Okay, this is the inverting amplifier. All right, let me fit the resistor here. This is minus. So this is inverting. And this is your RF and this is your R1 or Rin. Okay, this is inverting. This is non-inverting because V plus is not grounded. And also because you have a feedback loop. So check your V plus or your non-inverting input. Okay. V plus, the actual name is the non-inverting input. So if your non-inverting input is grounded, then we are talking about the inverting amplifier. If your non-inverting input is not grounded, like this one, then we're talking about the non-inverting amplifier. Okay? Right. So if it's non-inverting, part 2, show that the gain is 6, we can use this equation. If you want to know where these equations are from, once again, we have also recorded a proof. You can find it in the playlist if you have time to study this. If not, for exam purposes, you memorize first law. Okay? So gain is equal to 1 plus RF over R1. So you see the RF is here, the R1 is here. So this gain will be 1 plus 3.6 kilo ohm over 0.72 kilo ohm. Is it 3.6? Yep. All right, and if you press your calculator, this would be equal to positive 6.0. So proven. I'm guessing the mark for this is pretty straightforward. If you show the substitution here, you will get 1 mark. For this one, if you get the right answer, you will get 1 mark. Okay? So for op-amps, right, there are general equations. Do you need to know the proof? Yes. So things that you can memorize in op-amp, memorize, although I don't recommend, is the proof for the gain, is especially this one. This one has came out before, but I don't think that they can't ask this. So make sure you know how to find the proof for gain. And also, oftentimes they will also ask you to explain. So you need to figure out how to explain virtual earth for the inverting amplifier. And also to be able to state the properties of ideal op-amp. These are not asked in this question, obviously, but they can ask. It is covered in your syllabus. And also to be able to say the benefit of negative feedback. So normally if they ask you these things, it's about 3 to 4 marks, and it's actually quite a lot leh. 3 to 4 marks is about, it will be at least 20 to 30% of the whole question. So I hope you don't just focus on the analysis, things that you need to analyze. You also, if you are able to, look at the explanation. At least this one is easy to get live. If you don't know how to, if you don't have time to watch the proof, it's okay. But this one all pretty straightforward stuff, okay? So I will not go through them, but these are things that you should review if you're preparing for your exam. Next, oh, this is a sketching question. At time t equal to 0, the input V in is 0, okay? V in is gradually increased with time t as shown in figure 7.2. Alright, so we know that gain is actually a multiplying factor. When I say multiplying factor, I mean gain is like the ratio of V out to V in, which is equal to 6. Meaning to say, right, I will multiply my input by 6. Output will be equal to 6 multiplied by input. So if I'm going to multiply my input by 6, I basically will make the line higher right here. Because this reading here is 1, and then this one would be 6. 1 times 6 is 6. Basic arithmetic. Okay, so let me draw that line for you first. I'm going to expect to get a line like this. Please use pencil when drawing in your exams. Okay. And if you're watching this, the live recording, feel free to talk to each other in the chat. Don't be shy. We are all trying to learn physics together. So this is 6. And some students will leave it this way and call it a day lor. Times 6 ma is correct. Wait. Always check supply. So whenever they ask you to sketch, this kind of sketch, for your V out sketch, very important, I draw a few exclamation points. Check the supply. have we saturated the op-amp? The op-amp saturates at 3 volts, meaning to say the most it can give you is 3. So, bruh, we can't get 6. This is sadness. Well, it's okay. If the most that we can get is 3, here is your VS, your supply, then this is where the graph stops. So here from 3 onwards, you draw a straight line. It is supposed to be 6, but unfortunately, I can only give you 3. And this part here will be not there. I mean, if you want to, you can draw a dotted line. Okay. So I'm able to multiply by 6 all the way until my input is 0.5. So at this point here, my input is 0.5. So 0.5 times 6 is 3. And that is the maximum output I can have. After that, it will be just 3, 3, 3, 3, 3 all the way to the end. Because the supply saturates at 3. So this is what we mean by saturation current. You don't have to write this during the exam, but I'm writing this so that you understand. This is where your op-amp saturates. Full lah. It is full. It's like, you know, you want to study 6 chapters, but after you study 3 chapters, your brain hang already. Oh, my brain saturates. So you don't get new knowledge. You still have 3 chapters. It's a sadness. It's okay. We all have limitations, including the op-amp. Alright, so where are the 2 marks? I'm guessing if you have this line, your gain is 6, is 1 mark. So when I say this line, especially this kind of Vout sketch, please make sure that you pass through the correct coordinate. So I think for this one, probably 1 mark is a line, a straight line. It's a line passing 0, 0 and 0, 3. Okay, so you have to pass this line. Is it 0, 3? My bad. And this line, this point here, it's not 0, 3 or you don't know the time. Passing 0, 0 and V out is 3 volt when V in, which is this black line here is V in. This purple line here is V out. So when V in is equal to 0.5 volt. So basically passing these true coordinates lah. You don't plot, no need to plot, just draw a line. Alright. Next mark is when you saturate at plus 3 volt. Okay? Because this is a non-inverting amplifier. So it will not flip to the negative. For examples involving the inverting amplifier, you can watch in the playlist. Alright, part 4. State how the circuit in figure 7.1 may be changed so that the gain of the amplifier depends on light intensity. If you want something to be dependent on light intensity, we will have to replace it with a LDR. So for 1 mark, I'm not going to write so much. I will just say replace the 3.6 kilo ohm with a light dependent resistor. Okay, so you can replace either resistor. You can replace this resistor with an LDR. You can replace this resistor with an LDR. It doesn't matter. It depends what you want the circuit to do. Do you want the circuit to turn on when it's bright? Do you want the circuit to turn off when it's bright? We don't know. We just want the circuit to change when light changes. So I can put the LDR in any of the position of the resistor. But don't flex lah. Write 1 enough. Okay. So this one would be B1. Alright, next. An op-amp is to be used to switch on a high voltage heater. Okay. State the name of the component used as the output device. So for op-amp, right, there are 3 types of output device. Okay, so if you're revising, make sure you, after this video, go and revise. Okay, so there is the LED, light emitting diode, the bling bling lights. There is relay, which is what we use to turn on another circuit. So the component that we will use is a relay switch. And the third one that they can connect an output of the op-amp to is some form of a voltmeter. Alright, so here, using the devices and the diode, a diode, so that the heater may be switched on, you want it to turn on, when the output of the op-amp is positive. Okay. So if the output is positive, right, and I connect this way, let's say I didn't connect anything. Here is 0 volt, here is positive. Current will flow from high potential to low potential. This is the direction of current flow, right? High potential to low potential. Like water, we go from high to low, like waterfall. So now we know the current is going to flow downwards. So when I draw my relay, and you see, this one is the switch. Okay, so the reason why we use an op-amp to turn on a switch is because we don't want to touch the high voltage heater. Okay, we do not want to touch the high voltage heater. And the reason why we don't want to touch it is because it's dangerous. It's mainly for safety. And also, we also don't want the high voltage heater to reach the op-amp, because the op-amp is actually a very sensitive circuit. It's a bunch of semiconductors. It will spoil. Alright, so ideally we would like to have this not touching each other, a bit like social distancing in COVID-19. We need to quarantine the high voltage heater. Okay, so we want the current to flow down, so obviously we're going to put the diode this way. Okay, and then we will draw a box to represent the relay. And that's all you need to draw, I believe, but just give me a sec to make sure you are safeguarded. This is the relay. Most of the time, I will tell students, you draw a box is good enough lah. Because the CIE convention, let me pull the diagram from the CIE convention. CIE convention will normally draw the relay switch like this. Okay, where do I put? I'm going to put this here. Okay, so normally the relay switch is placed this way. So you can draw a box here, and I guess if you really want to label, you could label this one coil. Okay, so this coil is actually an electromagnet. This is actually a magnetic coil. They didn't draw, but inside here there's a magnetic coil. So when current flow through the magnetic coil, it will attract this switch, and this switch will close, and then the motor will turn on, or the high voltage heater will turn on. So this is a coil. Diode 1 is to make sure that current flow in the right direction. So current flow when V out is positive. If you want current flow when V out is negative, then you flip the diode. Okay, so this is D1. But you may notice that there's another diode here. So since this relay drawing is 3 marks, I will draw this diode as well, although they did say a diode, so it would be not fair for you if they expect you to draw this. Don't fire me, it's just my personal opinion. Okay, so then I would suggest that you add this diode, and this diode is for safety. Okay, what kind of safety are we talking about? Let's say, for example, you turn on the relay and you turn on the heater to boil some water, or I don't know why, or let's say you want to turn on the heater to heat up your room because it's cold. And then after that, you want to turn it off, right? Because, you know, conserve electricity, save the earth and all that. And when you turn it off, what happens? What happens when you turn off the relay? Do you think the coil likes the change in flux? When you turn off the relay, the coil will experience a change in flux, right? And then the coil be like, hey, we had this current coming down. Life was good. Why did you take this current away? So according to Lenz's law, the coil will try to induce back this downward current. But the current is not in the op-amp anymore. So if you want to draw this current from the op-amp will spoil because this EMF is very high. You turn off a switch, right? We go from got flux to no flux. So then it creates an EMF. So we have this diode here, so that this diode can recreate that recreate that current. So this one is what we call the induced, and it's a large induced EMF. Okay, when the op-amp is off, when there's no current, okay, when this is negative or when it's zero. You might be saying, why can't we just continue and take from the op-amp? Because op-amp can only give you small currents. Okay, so this one protect the op-amp from large back EMF. So this surge of current will not come from the op-amp, it will come from the ground. Ground is very safe. Okay, ground is the earth. The earth is safe. It can give you as many charge as you need. It can take as many charge as it needs. Okay, so I have also recorded an example video regarding this, so you can go and watch that. But I'm just going to draw this one here lah. As a student, I will draw this because I don't know where the 3 marks are during the exam. Maybe it's here. I don't know. I'm just going to draw everything, and I'll make sure I label my coil in case the examiner doesn't know. Look, it's a very large paper with many examiners, so you don't know what is a convention at where they are. So it will be very helpful for them if you label your stuff. Unless it is just a very general symbol like this one and this one. But if you also have anxiety around stuff, you can always label stuff. Not needed, but you can. It doesn't really crowd out the diagram. So this thing is 3 mark. I'm guessing 1 mark is for diode 1. Diode 1 in correct orientation. Diode 1 connected in correct orientation. Another mark is for the relay coil connected correctly. So between the diode and this thing. Okay. And if let's say they are nice, the other mark is for the switch lah. But it's very weird, right? If you have a coil, you don't have a switch. It's like you have Batman but no Robin. Okay? So, or, I don't know because I didn't write the mark scheme, or 1 mark could be diode 2. The one that protects against the large back EMF. So that when you turn off the current in this coil, I need to generate back EMF to oppose the change. That back EMF that is very large does not come from the op-amp. It can be drawn from the ground. Okay, so that is question 6. I spent some time explaining op-amp. Please make sure this is a very easy question. This chapter is very worded one. You study, got 1 question, at least 8 marks, 7 marks. Pretty good, right? Oh, 100. And there are not many things to study, and we kind of roughly know they will only ask these 3 circuits anyway. So if you understand this and you know other small detail about what an op-amp is, it's a pretty doable question. Just stay calm and don't study this thing last minute. Alright, that's it for this question.